Good afternoon, everybody. Welcome, welcome, welcome. Thank you so much for being here this afternoon. I hope you guys enjoyed your lunch. My name is Jill Becker. I handed my thesis in 2002, so quite some time ago. I'm a chemist by training, and I'm a proud member of the Harvard Griffin GSAS Alumni Council. So as someone with a background in chemistry, and I've spent my entire career trying to commercialize tough technologies at the intersection of chemistry, nanotechnology, physics, etc., I'm super excited to introduce and welcome Professor Evelyn Hu. She's the Tarr-Coyne Professor of Applied Physics and Electrical Engineering at Harvard University and co-director of the Harvard Quantum Initiative. Professor Hu received her PhD in physics from Columbia University and her BA from Barnard College. She has built a distinguished career in the forefront of nanoscience and materials engineering. Before joining Harvard, she served as a professor at UC Santa Barbara and as scientific co-director of the California Nanosystems Institute, following earlier groundbreaking work at AT&T Bell Labs. Professor Hu is a member of the National Academy of Sciences and the National Academy of Engineering and the American Academy of Arts and Sciences, and has received numerous honors, including the IEEE Andrew Grove Award and the James Clerk Maxwell Medal and the APS Mildred Dresselhaus Prize. Please join me in welcoming Professor Hu for her presentation, Opportunities for Quantum Technologies in an Imperfect World.
Am I on? Yeah, I'm on. Thank you so much, Jill. And thank you, all of you sitting here who've given up this amazing Saturday. And for those of you who live in the area, you know that 3 weeks ago, it didn't look like this. And so being able to be out in this kind of weather really is a joy. And thank you for joining me on this journey in quantum. Before I begin, you all must have some thought about what quantum means. So can I just hear, what do you think quantum is? Raji, not you. There's somebody here who has actually worked in quantum, I know. What does quantum mean to you? Just say anything. Spooky, weird. What does it mean to you? Spin. Spin. Great. You are a chemist, yeah.
Difficult physics on one hand, hype on the other.
Ah, the hype. Okay. Difficult audience. What else? Silicon? Subatomic. Very good. More. Steps. Yes? Energy bands. This is a knowledgeable audience. Where did you get it? How many PhDs? Yes? Spooky. Oh, what? Okay. Fast computing. And do you have an idea about why fast computing?
It's, using a different approach to computing.
A different approach to computing. So, unmanageable? Okay. So this is great. I'm glad that all of you have some experience and maybe expectations about what quantum is. You're going to see just a sort of broadest brush of what quantum is from a very personal point of view. It's something that's very relevant to what's happening now. And actually what's happening to now, you're all alumni of GSAS, something particular that is very relevant to GAS today. So what I've shown here as part illustration, if I can figure out, is a cover from The Economist. It shows some kind of super atom pummeling outside of a computer with a bunch of ones and zeros. So the sort of POW, the Superman image, and actually the ones and zeros all give an indication of the answers that you've given about what quantum is. So thank you for joining me today on a very brief journey through quantum. And it is the evolution of quantum, and it's a very recent evolution of quantum because many of you know that quantum started at the beginning of the 20th century. And here we are, lo and behold, the beginning of the 21st century. Or actually, we're heading into the middle. So I want to just briefly talk about some of the opportunities and why it's so hot now. I mean, it's been around since Niels Bohr and Paul Dirac and Einstein, a number of people, innovators, who lived a very long time ago. So why now? What unleashed the power recently? Some of you may know this already, so this may be redundant. I want to give you some access to the words we use to describe quantum, something called qubits, quantum computers, and then a little bit to counter the hype, the actual technological challenges that we face. And those technological challenges, together with this enormous promise, is something that my personal feeling, and I hope I'm going to convince you too, in the time that I've seen technologies developed, I've honestly never seen something where there's the conjunction of something still so blue sky, still so difficult, as some of you mentioned, and yet is out in commercialization already. If some of you know about Microsoft and Google, and IBM. So because of the tipping point, I'm going to very cleverly use that tipping point, this unique point in time, to talk about something that I hope will appeal to all of you as alumni of GSAS, a unique role for the Harvard Quantum Initiative here and a new graduate program in quantum science and engineering. And then I'm not actually going to talk about extensively about my own research, but I will give you a view of why I called this quantum opportunities in an imperfect world. Because my research actually deals with the imperfect. Actually, and I love it because the fact is I work with imperfect materials. But it's those imperfect materials that give rise to unusual opportunities for different kinds of qubits. So let's move ahead, and a brief introduction, my version of the opportunities of the quantum world. And some of you said, it's weird, it's spooky. So here's the weirdness of the quantum world. I don't know if you can see very clearly. Here's a tree. People, they look like they're cross-country skiing. Here's someone looking with amazement at somebody who apparently seemed to have gone through the tree. And this idea, this weirdness, is actually a good representation of the weirdness or spookiness of quantum. Superposition. Objects can be in two places at once. The entities of something like your own self that you protect, your limbs, the core, your torso. But apparently you can do this seemingly impossibility, still have the same integrity of the original object, and yet it seems that there's an interaction at a distance. So the idea of superposition and entanglement is that the right foot should know what the left foot was doing, even as it goes through the tree. So this idea of not only can you be distributed in space, but you maintain that sense of the coherent entity, separated by however long a distance. So to give you more of an idea, we like to use these ideas. The promise of quantum is inherently in information. And you may or may not have seen information represented like this in a simple world, in a simple way. We live in the digital world. Digital means we either have a 0 or 1. Lights on, lights off. We use spin up, spin down. So a simple representation of information is, in the simplest way, off or on. And that's sort of what we call digital two basis states. Basis states mean that this is the starting point of generating complex information from everything. So, but in the quantum world, we take these basis states and we talk about not a definite 0 and not a definite 1. We talk about a probability. We talk actually about something called a wave function. That means there's a fuzziness. Some of you know this very well. Jill, you know this well. I don't know how solid I look to you, but I'm actually a wave function, and I'm tapering off. You don't see me tapering off, but I actually extend much beyond what you see before you. And so the idea is that a quantum state, we call it psi, is a combination of these two basis functions with alpha and beta, but alpha and beta can be anything between 0 and 1. It can be 0.000009. It can be 0.999995. And what that means is this, the information that's represented by a state, given that we re-express the basis states in this alpha and beta that can be anything from 0 to 1, means the possibilities are limitless. The possibilities of limitless, that means you can have an incredible variation of alpha and beta. They have to sum up to 1. Some of you know this, anybody who studied quantum mechanics at any point. The possibilities are limitless until you make a measurement. Once you make a measurement, know what it is, it's all gone. But before it's gone, imagine the information that you can store. So here's a representation of a bunch of zeros and ones. In the digital world, the information is each one of these bits can be either 0 or 1. So when you gang them up, you do have 2 times 2 times 2 times 2. You have quite a lot of possibilities. And that's the basis of what's in your laptop, what's in your phone, the digital world that actually informs your life today. But in the quantum world, the information is coded in the zeros and in the ones. And I like to say, because of the possibilities, it's not just the zeros and the ones, but everything in between. It's almost like the information is encoded in the interfaces of the zeros and ones. And so the end result of that is, I'm going to show you an animation. Imagine the amount of information now you have at hand. Now, I wanted, before I show you a sort of animation to perhaps make you appreciate that incredible expansion of information, to talk about what made this possible? Why is it that maybe beginning 10, 20 years ago up to now, why is it that we think that we're at the brink of new opportunities for quantum now? And basically, Jill mentioned that I work in nanotechnology. I apologize for the appearance of some of these images. What you're seeing is that over a period of time, the scientific enterprise has made a tremendous expansion in capability to measure and control materials basically at the atomic scale, the nanoscale. And this is what I'm showing you is, this is a nanoscale probe. So each of these bright yellow areas is basically an atom. This is atomic mapping of materials. This is actually called a quantum gas microscope. And I know you can't see this very readily, but it is basically, it's a microscope that allows you to image single molecules or single atoms in a gas. And those molecules or atoms are held, they're called ultra-cold atoms. They're held by optical tweezers. So who knew? Who knew we could do that? But in being able to control materials and understand them at that atomic level, that's what made all this innovation and control at the atomic level and quantum possible. And you'll see more of this later on. So because of this, because of superposition, because of the information that exists at the interfaces of these zeros and ones, it means that in a quantum computer with only 300 qubits, 300, and I'll give you a point of comparison in a minute, you can simultaneously store and evaluate more solutions. There is a sound that comes here, but you don't need it, than the number of particles in the universe. Now, this may seem like hype. Does anybody have an idea about the number of particles in the universe? It's changing. Some of you may know about dark matter, but roughly it's about 10 to the 80, 10 to the 90, so a lot. What is that point of comparison? This is part of the opportunity. So what are the opportunities? Just because of this richness of information that can be stored and perhaps accessed in quantum, this presages a profound change in acquiring, storing, sending, and processing information. And if you think about it, we're all about information. And this is not to detract from the humanities, the social sciences, literature, art, or anything. All of that is information. But think about how relentless we are in our need for information about our environment, about the news, about calculations, about streaming videos or whatever. So this allows us to do quantum speed up. We do superpositions to process many inputs in parallel. We use fewer qubits for similar computational complexity. We can store and communicate. We can use those superpositions actually for secure transmission of data. That is when I said you have infinite possibilities of information until you make a measurement. The thing about quantum is when you make a measurement, when you have a quantum system and you decide to make a measurement, you collapse it. Everybody knows you've made a measurement. You change everything. What possibilities could have existed, you've changed it by your measurement. And that means that anybody who took your stream of information and tampered with it up the line, you know, because everything has changed. Quantum sensors that are atomic scaled and can be multiply combined to get an incredible richness of information about the real world. So in short, it's what we sort of always ask for: faster, higher density, greater precision. And I put in parentheses lower cost because we always ask for lower cost. And whether we can get it or not, particularly with a new technology, whether you can get it or not is something I think we have to table for a while. So that's the opportunities, the first part. Let me give you some images to maybe, some of you may know these, but give you some images so you can tell your friends what a qubit looks like, what a quantum computer might look like. So these are old images because the area is rapidly changing. But these are some images. IBM is making superconducting computers. Google as well. Honeywell has an ion trap. This is a chip. This is a chip level. So it's much smaller that Intel worked on. That's superconducting. So except for this, which is sort of the heart, the meat, and I'm going to show you what qubits look like. What you see is a lot of hardware, and a lot of hardware that sort of may challenge your belief that this is going to be an easy, inexpensive technology. But we'll see. What does a qubit look like? And just to give you an idea, the intention of this is to introduce you to qubits, but to also tell you that right now, as people are trying to make advances in quantum computing, quantum sensing, quantum simulations, there are an enormous choice of physical manifestations of a qubit, and the jury's not out yet. So these are photons. By using photons, I should just show you scintilla of light, because photons are units of light, but these are the chips that harbor photons. Semiconductor systems, so semiconductors like silicon or materials like that. Cold atoms, so this is a representation, but the intention is that these are individual atoms that are held in place, trapped ions, and superconducting circuits. But this is just to give you an appreciation that right now, there are a huge number of choices for what the real big quantum computer will be. And these are all being worked on by a variety of companies as well as academic entities. And to hopefully help you appreciate that point now, as we're on the precipice of what promises to be a technological revolution, I want to take you back. Some of you may know about this, about a different information revolution. So this is back to 1948. This very humble looking structure, which was probably about this big, is the first transistor that came out of Bell Laboratories. It was actually not silicon, it was germanium. This part here, this triangle, is a piece of plastic. This is a paper clip. The heart of the material is germanium. It's right here. It really did look like, when in 1948, this was the basis of a Nobel Prize, but in 1948, the inventors were enormously happy that they had made what is called the first solid-state electronic switch. But who would have imagined then that this would be the basis of a technology that dominates our day-to-day life? This is old technology, is 2017. This is a single-chip cloud computer. This is probably a few millimeters on a side and has trillions of these transistors. Now, I want to show you this because part of the story of silicon and silicon transistors, I think in many ways have led us to demand more and more of new technologies, have led us to sort of insist on change that comes every six months with more capability, more information handling, processing, and that's cheaper. But something to remember is that from 1948 to actually the first integrated circuit was 1961. That's quite a lot of time. This took a long time to develop. It took, and so it's about 60 years to now. The first applications that people thought of for transistors were actually for hearing aids. Because when this technology came up, people honestly thought there's something here that's important, but they honestly didn't know what to do with it. And so this technology has had the benefit of 60 years or more of development, beginning to find out what these switches could do. And in parallel, as we learned what the technology could do, begin to understand how you could speak to them. What kinds of rules would you give to them? What are the architectures? What are the algorithms that enable these transistors to work in synchrony to actually create a purpose? What we have now is actually not one material. We have a plethora of choices. We have, it's going to come up in this next slide, we have so many more unknowns, although we have tremendous possibilities. So with these opportunities come challenges, and very different challenges from the last sort of information explosion. Here are our ones and zeros again, and here is the information between the ones and zeros. One thing that's so tremendously difficult, and this is what this triumph of recent control at the atomic level is, these are quantum states. So what is a quantum state? Somebody said spin. Here's a top spinning. So imagine this top can have two spins. It either spins clockwise or counterclockwise. But once you establish the top in one quantum state, either clockwise or counterclockwise, your role, your job is to make sure that your spin keeps its spin, polarization we call it, over how long? Long enough so you can do some computation. Now computations can take microseconds, 10 to the minus 6 seconds, nanoseconds, 10 to the minus 9. That sounds like a generous amount of time, but in point of fact, think about keeping an electron spin in one polarization when it exists in a material that has all kinds of electrons and ions whizzing about, maintaining, we call that coherence. So this is a critical challenge. Beyond that critical challenge of basically the physics alone, keeping that coherence, whatever hardware system you choose, what hardware system do we use now that we have many choices? Where do you invest? How do you ensure, and I know that I've spoken about in an imperfect world, but it seems like we really need perfection. How do we ensure perfection at the atomic level? How can we have a few qubits here. We have one example of a spin here. How can we scale up to system level sizes from the atomic level? And what master plans do we impose on quantum systems? How do we talk to them? How do we talk to them and correct errors when as soon as we touch them, they collapse into a state that maybe we didn't intend? So those are the challenges, and those just a few of the challenges that we face now. And then I want to now, having introduced those challenges, make the point again that I made earlier, that we're at a distinctive tipping point. And this, I tried to illustrate this by this diagram that I constructed with the help of ChatGPT. So the intention is, I asked ChatGPT to draw a diagram of a quantum computer, and so here's a quantum computer, scaling up into manufacturing in a big way, primed for success in the marketplace, but within a blue sky atmosphere. So all this twinkle in the back and research and the microscopes, the idea is this is both tipping point and anomaly, because we have major companies going out into the marketplace now, promising the first quantum computers, promising something called quantum supremacy. And yet, I hope you understand, we worry about keeping spins in one state for microseconds or nanoseconds. One spin out of maybe, even if 300 qubits is enough, you want more than 300 qubits. This unusual conjunction of blue sky with first adopters in the commercial world willing to go out and step out and say, we've got it. And we actually haven't fully identified the killer apps. It's not going to be hearing aids, but we don't know what are the algorithms, what are the actual computational, even if it's computing, where there is a host of computational capabilities that are really going to outperform classical computers. And it may not be computing, it may be something we call simulation of the real world. And I point this out because lest you think that I'm talking about something that is irrelevant to all of you, to all of us sitting at Harvard, that has just gone crazy in the commercial world, so why even bother? I want to make the point that now more than ever, it is a role of academic programs to not step back but to step forward to help ensure that this translation from amazing possibility to real applications takes place. And so I'm not selling HQI, but I just want to show you a couple of slides on the Harvard Quantum Initiative. This is, I think, what motivated a group of us here at Harvard. Actually, long before 2018, we've been working on this long before that 2018, but in 2018, the Harvard administration took the deliberate decision to say, okay, we believe you. It looks like there is something unusual going on. You have an unusually rich legacy and actually a history of collaborating together. So there are a lot of important pieces that go forward in this. Here, we'll give you we'll sort of bless you, as you can call yourself, the Harvard Quantum Initiative. We'll give you a little bit of funding, and the initial intent was for 3 years of funding. Go see what you can do. And I will just give you a brief brush of what we've done since. So the idea behind the motivation that we actually spoke to the administration about was we needed to exist as a community with resources to build the community further for the longer term, to maybe recruit young faculty who are the first working in a new collaborative environment, to create a new first-of-a-kind education program that would mix science with engineering in a way that hadn't been done before, so that the new generation addressing the problems that we're facing would have the full capability and understanding to attack those programs. It is multidisciplinary in a major way, but it is multidisciplinary in a way that also means we have to have new models of collaboration, not only among academic units, but with industry and with government labs. And in short, our mission is to transform engineering, science, research, and education for the long term. This is our mission. And again, rather than reading it, I'll just say a reiteration to give us the wherewithal so we could build the foundations to move the community forward. It is today 2026. We succeeded with that initial investment beyond our wildest hopes because of the generosity of many people who believed in our vision. In particular, and I invite you actually, probably not today, but if you're around campus, we have a building, the David E. and Stacy L. Goel Quantum Science and Engineering Building. It is not the only physical location of this widespread community, even at Harvard, but it's so important to have one physical manifestation, one community place. We have new instructional labs, we have new shops, we have new labs where we can bring in new faculty be hired, and we can bring in visitors. It is so important to have a physical signature that, yes, we're there, and we want to bring other people there. I'm just going to take because this is GSAS Alumni Day, I just want to say that I hope that you are all proud of the fact that in 2021, the entire Harvard faculty voted positively on this new PhD program in quantum science and engineering. And just very roughly, why did we feel that we had to create a brand new PhD program? We believe that just because of the content, because of the mixture of computer science, electrical engineering, different kinds of computational schemes, as well as physics and chemistry, that we needed to have a tightly integrated course for our students from day one. And not only that, we had to make this program accessible to students who concentrated or majored in computer science, never took a quantum class, concentrated or majored in electrical engineering, concentrated in physics, but had no idea what a circuit was. We had to make this program accessible to them and create this so that from day one, they could be lockstep in educating each other, communicating to each other, and then also, I hope you appreciate this, as long as we were crafting a new PhD program, maybe we should get it right. Because the PhDs of today, I don't know what your experience was like, we need to be more cognizant of outside opportunities, not just academia. We needed to be more cognizant of professional opportunities for our students. We had to be more cognizant of the importance of advising and mentoring from day one. And we had to be more cognizant to encourage our students to come in and learn to communicate in various languages. They're developing the new dialects of quantum technologies to talk to each other, to talk to the people that they're going to teach, to talk to the people that they're going to convince for funding, to talk to industry, and so on. So that is basically, we just finished our 5th year of admissions for this program. The last slides, the last information that I want to show you, and then I think we can end early, I hope, and have lots of questions. My research focus, and this is the real reason I used the title I did, which was Quantum Technologies in an Imperfect World. And so I'm going to use a model. What I actually do is work on to think about the following questions. I've given you some broad brush introduction of what qubits are. They are the transistors of the quantum world. They are sort of like the switches of the quantum world, except they're so much more fragile than transistors. But if you ask the question, what if we could create qubits that actually have those long spin coherence times? So imagine again that spinning top, clockwise, counterclockwise. It stays there maybe forever, or you give it a little push and it stays longer. That actually spin states, those quantum mechanical states, could be initialized and read out by photons. What does that mean? Somehow, when you start out with a bunch of qubits, you may want to say time t equals 0. I'm going to set 1, 0, 0, 0, 0, 1. You want to set the starting parameters. And you want to do it easily because you're not going to go in with your hand and switch each atomic spin. The idea that we can use light, that light interacts with these atomic level, less than atomic level, quantum mechanical units of information makes it is an easy, sort of workable way that we believe we can scale up. And that where we could actually create the qubits within their own protective isolating environment. And I'm not going to give you a lesson on semiconductors. Somebody said band diagrams. Imagine this is a crystal. It's a semiconductor. There's something notable about semiconductors that they have a band. So my right hand, my left hand define the band. Within this band, nature gives us, in a perfect material, there are no allowed energy states within this band. And if you have an energy band, if you have an energy system where actually you have something that you deliberately put, something whose state is within the band, below my left hand, billions and billions of electrons. Above my right hand, 100, 1,000, 10 to the 6 electrons. The point is, the electrons up here, the electrons down there, they can interfere with that precious quantum mechanical coherent state of a state in here. If I create the right material, with enough of a band gap, then maybe that's what I mean by the protective isolating environment. And so I'm telling you the wish list of a scientist or a nerd. If I could have this all operate at room temperature, I don't have to cool it. I don't have to generate a lot of heat. Wouldn't that be amazing? And what is the answer? The answer is, I'm showing you a material. This is a material, it's not silicon, it's called silicon carbide. What I'm trying to show you here is this has a different regular structure than this. But what this has, this perfect silicon structure, this is a crystal structure. And most of the time we work with materials. When we work with materials and want to make devices, we have the idea that the more perfect it is, with every atom in place. So for those of you who know, the black are the atoms, the gray are the electrons between atoms that also serve as bonds. And it's as if I took this material and I said, look guys, you think this material is good. Let me just remove an atom. Let me just take an atom out, which is what you see there, the hole. And it's actually those defects, those vacancies that are actually the heart of the information sort of carried by a qubit. So these are atomic scale entities. So we can make many of them very densely in a semiconductor. And they do have this amazing, they've been shown to have an amazing spin coherence. And the thing about the spin coherence is there is a related photon, and it has to do with the energy levels. There's a related photon so that when you have spins prepared, like all spins up, for example, you get a unique optical signature. The spins stay in the material. So that spin coherence has to be local to the material. You want to do quantum mechanical manipulations, you want to do entanglement, you want to do superposition. You really can't take the spin away from its home, but you can send that photon long distances so that different spins in different materials can communicate, can entangle, can superimpose, can be the basis for quantum mechanical operations. And then just to show you that the idea is to put a spin in something called a cavity, spin in something called a cavity. A cavity is like a cavity of a laser. It's what allows, there's a semiconductor laser inside this pointer. It's a sort of bespoke amplifier. We can make these little amplifiers, and you can imagine that they're very small, so that we actually amplify the unique signature of the qubit. We can send the optical signals from one qubit to another, so we can entangle them. We can make them carry out quantum mechanical operations. So this is the beginning elements of a quantum network, the beginnings of utilizing these atomic scale qubits. This is one of the areas that I choose to work in. My colleagues at HQI work in all of the many manifestations of different quantum technologies. So we're at the end of this very short journey. I hope I've given you the first introduction to opportunities and why now, what unleashed them. A little bit of a pictorial familiarity with qubits, quantum computers, what they might look like. I hope one of the things I want to convey to you that this is a really exciting time. This is an unprecedented time, an unprecedented tipping point. Because honestly, the mixture of blue sky and the willingness to go forward with commercialization, I think benefits us all and gives me hope for proceeding with further science, engineering, technology, and realizing the promise of some of these quantum technologies. I use that very subtly as an introduction to what's going on here. And I welcome any of you who would like to find out more about HQI, come visit us. It's 60 Oxford Street. Please do so. And then just the touch of the imperfect that delights me. I'm always delighted when I find something that, just seems completely contradictory in nature that actually blossoms with promise. So thank you, and I'm happy to take any questions you have.
Thank you so much. Do we have time for questions?
Oh, absolutely, absolutely.
Hello, thank you for that introduction to quantum. How does this technology work with the types of silicon chips that are taking over AI right now by NVIDIA and other people? Did they replace? Can they work with these chips or not?
That's a great question, and there are many manifestations of your question. So first of all, how does it work? I'm going to take your question forward and you push back. So how does it work with silicon chips? What happens with what's going on with NVIDIA now? The tremendous need for those the chips that NVIDIA is generating. Those chips are old technology. Those chips, part of it is getting enough of those chips. Those chips actually suffer from one of the issues for classical transistors, as wonderful as they are, because if any of you have ever felt your laptop heat up, if any of you have ever felt your phone heat up, it's because your chips are dissipating. Those are electrons going back and forth. And electrons moving back and forth, if they're not superconductors, they generate heat. So number one, the chips we have today and the classical computation requires a tremendous amount of energy. Will quantum take over NVIDIA's chips? Probably not. My guess is probably not, just as we looked at the history of technology of integrated circuits. Silicon up to now, and if for those of you who have studied in any way sort of paradigm-changing events in technology, the silicon technology is so powerful that it's hard to get away from it entirely. So over the years, there have been other technologies that have been proposed. There's something called silicon photonics. So using photons instead of electrons means that there's less dissipation. There are silicon photonics technologies. They have their own power. They're not going to take over. They have a niche application with respect to silicon. There are other kinds of technologies that have niche applications. So I assume that, the idea that quantum computation could happen rapidly, fewer qubits, we hope with less power dissipation, but right now a lot of the quantum technologies require cooling. So there's that different energy cost. If it is to succeed for AI, if computation for AI, I think it will have a niche application. We'll see it progress. I should also note that there is AI in quantum systems, which has different ramifications. So different ways of doing those computations or different ways of adding AI into quantum computations. Is that? Okay.
So how many qubits can you assemble at this point? And Jensen Huang was known for making the comment it'll be 20 years before quantum computers. And then there were executives from companies that say, no, we're doing computations right now. What in fact are they doing right now?
So number one, the major companies like IBM, like Google, and IBM was one of the leaders in this, they're increasing the number of qubits, but what they've done, and this is very smart, is they have little teaching sets. So there's something called Qiskit, Qiskit. They've open sourced this so that a whole generation of researchers and students, actually high school students, there are quantum hackathons now, can get used to the different kinds of manipulations that you might use in a quantum. So you can work on these systems, and they may be simple systems, but you can learn, actually you can begin to learn the language. So in classical computation, there are simple logic gates. There's equivalent out there on a variety of actually commercial quantum machines. I want to tell you a story, and it seems like I'm bragging about Harvard, but this is true, and it's not my work, it's that of my colleagues. If you had asked anybody, let's say 5 years ago, 10 years ago, out of all these qubits that I showed you, out of all these technologies, which one is the most likely, or which 5 are the most likely to go into commercialization first? A lot of people, and this is IBM, would say superconductors for a lot of reasons, because superconducting technology has gone out earlier. Other people would say ions, or they have sort of quantum dots in silicon. There was a National Academy studies that was released 6 years ago, and they talked about the 5 most promising technologies in the next few years. What was not even on that list is one of the sort of highest qubit technologies today. I think they have 193 qubits, and it is a company that came out of Harvard and MIT. It's called Quera, and it is cold atoms. And for me, who knowing what I know about the field and how difficult it is, so cold atoms are, you just take these atoms and you hold them by an optical tweezer, and you have these arrays of atoms, you move them around, you make them interact with each other. I would have never guessed that this is the most promising technology today. Quera has, actually, Quera started here. Quera has its headquarters nearby, but it's also actually sold machines globally. So to go back to your question, ironically, Quera has right now maybe one of the highest qubit counts. And for many people who understand, you understand why, because decoherence, it is low temperature, it's held by optics, but they're atoms. So sort of in the right environment, those atoms stay atoms. They stay qubits. Decoherence is very hard. Those platforms, they've already demonstrated error correction, different kinds of logic. And what are people doing? Even earlier, less advanced technologies, the companies are very smartly, and Quera does this too, make their machines available to the general population to play around with algorithms so that the whole research community can learn, what is the killer app? What can we do with it? What can we begin to do with this kind of logical manipulation that we couldn't do with classical?
Hello, thanks for the intro. So you have a very good metaphor of the transistor, which was invented in like 1948, right? So, which is a kind of qubit. So, but we know that the first personal computer was invented until like 1974, or Tarr 8800. And then Microsoft was founded in 1975, which is about like 26 to 27 years after the first transistor was invented. So my question for you is, if may not be a perfect parallel, so what year we are now in the history of quantum computing? Is it like 1948 or 1968? Like how far is it from like the personal computer, the Microsoft time?
That is a great question. I'm a professor here at Harvard. If I had that answer, I might not be a professor here at Harvard. And it's a great question, and everybody asks those questions with the onset of a new technology. But here's the thing. Here's the thing we have to understand. we think that technological revolutions or technological progression, we use what we've known from the past to anticipate what we can expect from the future. But when all those paradigms, many paradigms at once, are shaken, and also, we have different expectations from what we've learned by one technological progression. We have greater impatience. We have actually the benefits of all the information. Now, what do we have in terms of projecting? We have new tools, but in terms of projecting, we have communications at a global level about innovations. We have the capability of now we can use AI to help designs, to do inverse designs. We have so many other tools that it is hard to predict. That, I think, in some ways, our limitation. When we think about transistors and progression, if we think about classical computers and we want to understand what quantum computers do, we are not thinking broadly enough. Because when we think about quantum computers, we think about doing everything classical computers do, but maybe it's a little bit more secure and maybe it's faster. But that's wrong. I don't know the answer, but my feeling is it's wrong to think about that way. We need to really break out of the box in order to, so I won't make an extrapolation because I don't think that's useful. I think people can't help but use the past to make a prediction of the future. But as long as we keep using the old ways to think about something that is mind-boggling different, we're not going to get those sort of game-changing ideas.
Is a cold atom the same as a neutral atom? Are those same terms? Okay.
These these are neutral. These cold atoms are something called Rydberg atoms. So they're atoms that have been excited to a high level. These are nuances, but they are neutral. Yes.
Okay. So in the digital computing, there's a focus on the speed of hardware and the advance of the speed of hardware. But what really happened is it was the speed of the hardware plus the constant improvement in algorithms. Saw this again and again. So the massive increases in computing power were driven by both. You really see this now in AI, where it's just a very exciting time to be a computer scientist because the algorithms, or if you're the sort of computer scientist, it's just a golden age of algorithms and making everything faster on a monthly basis. It's easy to look at for a someone who has the number of qubits. Is there a way to, what would you look for if you're trying to get a sense of how fast this is moving? What advances in algorithms would you kind of look towards? How does one stay on top of the advances of algorithms, and what sort of things would you measure?
So that's a great question, and that's the point I wanted to make, that with transistors, there was this long time frame as we began to understand and we didn't go into digital transistors immediately. I mean, it's just a lot of analog, and then when you had digital, you began to think, these are the kinds of rules I can impose. So let me say a few things, and that's why I want to say one thing. The more that we have these test systems out, the more likely we are going to be able to generate the algorithms. As much as you would like to say that the algorithms, the rules of operation, we'd like to say, the rules of behavior, like the rules of warfare should apply globally, no matter what the local culture is. People might like to say it's hardware agnostic. And that's largely what algorithms and architectures are now for today's circuits. But they can't be. So what we've already learned, let me give you an example. Once you begin to have an actual system that the computer scientists can begin to play with, you learn different techniques. So this idea of error correction and actually the idea of readout, once we had these cold atom systems, they discovered that they, rather than taking a physical, I hope you, you're sort of impelling me to go into my nerdiness. Instead of having a physical qubit, I said one physical qubit, you make a measurement, it's collapsed. They learned that I'm going to use 6 or 10, a cluster of physical qubits. I'm going to call it a logical qubit. A logical qubit, I can tickle a logical qubit. I can tickle it so that its state doesn't collapse, but I can begin to nudge it or correct its error. So what I want to say, the point is that until you really cannot, my belief is that architectures and algorithms cannot be hardware agnostic, even though a lot of the literature today is, because you can just read quantum mechanics and it is. That until you actually face a real system, you won't come up with the insights like, aha, we can do this. The other thing is AI is amazing. Architecture is amazing. My personal feeling is that, I think at least when I look at what we offer as universities, and this is some places more than less. Some of you know that in the past 10 years, more than 10 years, 20 years, there's been this sort of large-scale stampede for students to study computer science because of many reasons, and probably because of the job market. That's beginning to change now a little the other way. My belief is if you think that you can freeze hardware development and continue to innovate just with algorithms, we're lost. Because until we have new hardware and new instrumentation, you can implement all the hardware you can, but at some point, those units are not going to move and behave in the way you want them to.
We have time for one or two more questions.
Sure. So you, I guess I'm a little bit confused about one element. So you mentioned qubit. If there's 300, you would have 10 to the 80 bits, basically. Why isn't it infinite? If you have an infinite states combined, alpha and beta, what is the threshold? What is the limitation on the amount of information in one qubit? Where does that come from? Does that make sense?
What I wanted to, and thank you, it is a complicated question. The thing is that, and there's a way of representing it. So we have 2 qubits like this and we combine them, and the coordinates, alpha and beta, it's not just 1 or 0. So if there were just 2, you'd be like this, like this, like this, and like that. They're 4. All right. The point is that they can be anywhere in between. And and we use different basis spaces. So, they have a relationship to each other, but they have a relationship in absolute space. And so if we were to map that, we could say that there's basically a wealth of information between them. I don't know if that makes it any clear.
I don't know if I understand the answer, but
okay.
This is very interesting stuff. Obviously, it's research. Obviously, we need to invest in research because we probably don't even know the right questions to ask. And as you pointed out, as you progress, you change the questions you ask. Right. But what is the map of questions that we're currently answering? I'll give you an analogy. My father worked in plasma physics in the 50s. I worked in a plasma group in the 70s. We still don't have fusion today. But some of the questions are perennial, like how do you contain it? How do you inject fuel? How do you capture energy if you do get a fusion reaction? What are the questions? I mean, you mentioned some of them, like how do you keep coherence? How do you put information in? How do you get information out? How do you transport coherence across distances? I mean, those seem to be some of the questions. How do you see the map of the research questions that we know about today?
That's a great question. And, I want to just say that there are countless roadmaps. So if you divvy it down, there are the broad questions like coherence. There are broad questions, a very broad question like error correction. How do you do error correction? How do you even understand where the errors are? How do you know where the errors are? What is the role, and this is for any technology, what is the role of noise? What is the role of noise to these very sensitive units of information that somehow, on the one hand, you keep them away from the outside world. On the other hand, there are actually ways that people have said, well, actually let them interact with the outside world a little bit. It's sort of average. So there's a whole bunch of things that go there. There are these broad questions about, just keeping all those qubits in a way that are well behaved in the way that you know. Then all those questions about algorithms, people are still doing, there are some algorithms that were early decided to be, you have a decided advantage. People working like crazy, and this is hardware agnostic, to see if there's the next one. And there are tests being done all the time. Is this really quantum supremacy? Is it not? You say, here's an example that classical computers can't do it. And then somebody actually pushes the limit of classical computing. And so this is back and forth. So there are these issues. And again, we're maybe asking the wrong questions. How is it faster? I can tell you, some of the things that people are talking about in terms of, can we actually do more rapid, let me talk about quantum simulation. You asked me the question, someone asked the question, are they neutral atoms? They're neutral atoms. People are doing cold molecules. People are doing cold charged particles. And the reason cold charged particles, because cold charged particles interact in a fundamentally different way and can simulate some materials. So what if you made a quantum simulator? The ability is to get everything, get everything in a starting setup, and then trust. So you have to have charge for this because electrons have charge. You want to model the behavior of a real physical material through a simulation. And the simulation in the qubits, if the qubits authentically reproduce quantum mechanics in a way that we can't do, in a way that we can only add little corrections if we were to do a computation with classical computer. If you can really just set things up and just let it go, maybe we could simulate. We could just look at the end and simulate. But, what are the questions? It looks like we may want to go not just one material, not just superconductors, not just ions, not just cold atoms. A reasonable way to go is hybrid. And that means that the components have to talk to each other. So we need interconnects. We need translation tools. And that's another big question. So there are countless roadmaps that are being generated.
I have a simple question. Where's the input-output for computing? Your input and output for your quantum computers?
It can be as simple as you want.
Yeah, I see. Is it laser?
Sorry?
Are you using laser?
The example I gave of qubits, you can use a laser. A superconductor, you wouldn't. So a laser generally is at optical wavelengths, and so maybe the information is a photon or a photon state, right? Then it could be a laser, or it could be multiple lasers. If it's a superconductor, you have a radiation, but it's at a different wavelength, so we don't really call it a laser. So it's some signal. It could be an electromagnetic signal. It could be an electron signal. In the same way, it's sort of, not to use analogy, how do we get an answer from a classical computer? It's basically a lot of transistors switching on, off, on, off. At the end, it could be a simple answer, 2. So it's how you code the information, and you have an expectation of the information stream. And you have an expectation of the kinds of answers you want to get.
Okay, fine.
All right, well, I don't have a microphone, but just to give us a sense of where we're at. You know, I mean, one of the things that people mention computers might do, you know, is be able to come up with prime factors of large numbers. So if I ask the question of take the best one at that, maybe it's Google's with 100 qubits. I mean, what kind of numbers have been factored with quantum computers at this time? Like 35 into 5 times 7, you know, or what are we talking about?
So I don't know quite the answer to your question. There is something called Shor's algorithm that elicited a lot of excitement. Shor's algorithm says that in quantum computers, an advantage is that you can use quantum computation to get very rapid factoring. I don't know if I don't think the machines have been benchmarking against Shor's algorithm. What has happened in terms of quantum supremacy is that different companies come up with an algorithm that are generally, and that's why there's nothing unambiguous in terms of who's won and are we there yet. Generally, a company will define a particular algorithm, a particular set of algorithms, and say that we've done with the ARM machine work has been able to do this more rapidly. So it's not a simple question. Shor's algorithm is one algorithm that we know can be implemented on quantum computers, but that's not what's being tested because you're not going to invest, even though it's interesting, it's not enough to drive a technology if you can just factor faster. And so we're looking for other algorithms that have the potency of Shor's algorithm.